All right, guys, in this lesson we're going to be looking at confidence intervals for regression slope, and our objective here is just to construct a confidence interval for regression slope. However, before we get into how to construct that confidence interval, we need to go over a few formulas. So first we need to understand that we're finding a regression line, okay, or we're working off of a regression line basically. What we want to do is we want to determine or guess what that population regression line actually is based off of a sample regression line. So those are the two categories that we're really going to be looking at, are population and sample, when it comes to all of these formulas. So first we need to understand the regression line formula itself. If we're looking at the sample regression line, then that's going to be y hat is equal to a plus bx, where a is our y-intercept, and if we wanted to find our y-intercept, we could use this formula, and b is going to represent our slope, and that's going to, if you needed to define b, you could use this formula right here. But that's essentially going to represent our sample regression line. Our population regression line, alpha is going to represent our y-intercept, and beta will represent our slope. And those symbols pretty much stay consistent with all other formulas and everything else that you see in these problems. So it's kind of good to understand what each one of those are as far as your population and sample regression line formulas go. So that should take care of those. Your standard deviation of residuals is going to be represented by S. Your standard deviation of slope would be mostly, if we know our population variables, then we can just go ahead and determine the standard deviation of the slope right here. However, most of the time we don't, and so this is the formula that we're going to be looking at predominantly, is the standard error formula right here. So this is the one to kind of keep an eye on. If we're looking at critical values for our population, if we know our population values or some of them, then we would use Z. If we are just working off of our sample, which most of the time we are, then we're going to look at T over here, because at that point in time we're looking at our sample slope right here minus whatever our population slope is divided by the standard error. And then finally, our degrees of freedom is going to be our sample size minus 2 in this instance for our regression slope. So the steps for solving these problems are very similar to how we would solve any other confidence interval problem. Really the only difference is that we are going to have to state a little more than what we normally would in the plan portion of this problem. So when we're looking at the state portion, all we need to do is identify the population and parameter. So the population is whom you are asking the question to. The parameter is what question you are asking in this case. We would not use a hypothesis for confidence intervals. That's only for tests when we're looking at regression slopes. Then we need to state our conditions for reference. And remember that we are kind of concerned with this liner acronym right here, and those are the ones that we need to test, or all the conditions that we really need to test in this case. So first we need to check for linear. So is the true relation, or the true relationship must be linear for that regression slope. It must be independent, so the observations must be independent of one another. 10% condition on sampling without replacement. It must be considered normal, and so for each value of x, the responding values of y must follow a normal distribution. You must check the equal standard deviations, and so for each value of x, the normal distributions for the responding values of y must have the same spread, and they must be considered random, so the data must come from a well-designed random sample or experiment. And we'll look at examples of some of these, because some of these are fairly easy to tell. I would say normal and equal standard deviations are the ones that are going to be a little more tricky to tell, but if you know what kind of graph you're looking at, then it'll be okay. Our do step is going to be to identify the confidence interval and calculate the critical value. So again, here, let's just write this out. So this represents your state, this represents your plan, this represents your do right here. And so we need to identify the confidence interval, calculate the critical values, and so really I believe that all we need to do is state our confidence interval, really, with our degrees of freedom at this case. I really don't. I mean, for the AP test, I would say, yeah, you might want to put it in this formula right here where you give the slope, you give whatever the t-value is times the standard deviation of the statistic if you can. But a lot of this can be found in the calculator using a fairly easy function in that. So I will show you how to do that in just a second. And finally, the last portion is going to be our conclude portion right here, where we state the answer in context of the question. So we are, whatever confidence level, confident that the true parameter lies within the given range. Again, our confidence interval gives the range of plausible answers, whereas our confidence level is the percentage of confidence intervals constructed in the same manner would capture the true parameter, basically. So that's how we would state that answer in context, basically. But that's a lot. We've done a lot of this, so hopefully most of that process should be a fairly easy review for you. So let's take a look at this example real fast. Earlier we used Minitab to perform a least squares regression analysis on the helicopter data for Mrs. Barrett's class. Recall that the data came from dropping 70 helicopters from various heights and measuring the flight times. Some computer output from this regression is shown below. We checked the conditions for performing inference earlier. So, and this is kind of a build off of an example from the last lesson that we looked at, but this is essentially your computer output or your Minitab output right here. Now, there are a couple main values when we're looking at this that you really need to kind of keep an eye on. The first one, and most of them are going to be concerned under this coefficient area right here. This value right here, this is going to represent A. Okay, so that constant value represents essentially your y-intercept at that point. So if we are given Minitab and we're asked to construct a regression line for this, that would represent A. So it would be y hat is equal to negative 0.03761 plus the second value represents your slope, so plus 0.0057244x. That's essentially your regression line at that point based off of this sample. So those are two, so this represents B right here. Those are your two kind of important values right there. The third important value is going to be represented by this right here, and that represents your standard error or the standard deviation of this. So your standard error is essentially just 0.0002018. Okay, so that's those are the three values that I have seen the most as far as a lot of the problems that we've been that you will look at in this lesson. So just kind of keep that in mind, that that first value under coefficient represents your A, the second one represents your slope, and the third one on the right represents your standard error or standard deviation of that slope. Okay. Now, with this example, first we want to find the standard error of the slope and interpret it in context. Well, we know that that standard error is going to be that third value down here. So from the computer output, we know that the standard error at B is 0.0002018. This means that if we were to repeat this experiment many times, the regression slope would change by about 0.002 centimeters from the true regression slope. Think sample slope is pretty accurate. If we were to say that the sample slope is pretty accurate to the population slope. And then if we were going to calculate the 95% confidence interval for slope and show our work, since we've already verified the conditions, we can calculate that confidence interval using our formulas, and we can use our calculator to help us find those values as well. So if we were going to just use what we were given in this problem right here, we know that our statistic, when we're setting up that confidence interval, this is going to represent your slope, basically. And so that 0.0057244, that's your slope, plus or minus. This would represent your t-value right here. And then this, so this represents slope, this represents t, and then this represents your standard error right here. So right off the bat, we already know our slope and our standard error, and really all we need to find is our t value. Well, if we know that this is a 95% confidence interval, I know that I can go to stat, and let me check real fast. It's going to be stat. Or maybe, no, excuse me, no, not stat. Sorry, second vars, my bad. Sorry about that. Erase that. We are going to look at second vars and then find inverse t. Okay? And when I plug in the area for inverse t, I am basing it off of one of the tails of that 95% confidence interval. So I know that if I'm 95% confident, that means I have 5% left on each tail. Well, I only want one of those tails, so I take half of 5%, and that gives me 2.5%. Well, 2.5 is going to represent my area right here, so that's 0.025 at that point. Then we would take our degrees of freedom, and I know that since we worked with a sample of 70, my degrees of freedom is literally 70 minus 2, which gives me my 68 right there. Those are the only two values that I need to know to figure out my t value. When I plug those in, it gives me a value of this, and so I know that my t value is plus or minus 1.9954 at that point, or 55, whichever one you wanted to say at that point. So from there, I would be able to solve my confidence interval. I can interpret the 95% confidence interval in context. We are 95% confident that the true rate of change of the paper helicopter is between 0.0053 and 0.0061 seconds of fall time for each additional centimeter of drop height. If we were to explain 95% confident in context, we would say, if we repeat this experiment many times, 95% of the time, we will capture the true rate of change between flight time and drop height of the paper helicopter. So if we're asked to explain what 95% confidence means in context, then that's what we're going to do for that as well. Now let's look at another example real quick. Everyone knows that cars and trucks lose value the more they are driven. Can we predict the price of a used Ford F-150 Super Crew 4x4 if we know how many miles it has on the odometer? A random sample of 16 used Ford F-150 Super Crew 4x4s was selected from among those listed on Autotrader.com. The number of miles driven and price in dollars were recorded for each of the trucks. Here are the data. So we're given all of this data right here. So now we're not really given our computer output or our Minitab output. We're given all of this data right here. So how would we solve for that? Well, we're going to have to use a lot of this to solve for that. But let's go ahead and just start from the top in solving this problem. First, we want to state our population and parameter. Well, we know that our population is the pre-owned Ford F-150s, and our parameter is the rate of change in value per mile driven. So again, that represents our state portion of the problem. Now, from there, what we would need to do is we would need to go ahead and put in our miles driven into L1 under stat edit. So we would need to go to stat edit right here and start filling in numbers, basically. So L1 is going to represent our miles driven. L2 is going to represent our price in dollars, okay? And so once we have that, what we would need to do from there is we would need to go to stat and calc. So stat, calc, and 4 to find our linear regression line. And it's kind of important that we find that linear regression line based off of what's in our table, because that makes graphing our functions a little easier at that point. And so once you have actually calculated the linear regression line, from there you can then graph those functions based off of their residuals right here. So you can use residual when you go to second and y equals, excuse me, not that, second and y equals, in order to graph your plots at this point, so that you kind of have a good idea of what you're looking at, and you can check your conditions at this point. So what we're looking at now is we're going to look at the linear relationship, because remember, we're looking at liner. So we're looking at linear first. So the relationship is linear. Given there is no pattern in the residual plot. So if we are calculating our residual plot, which is this right here, you'll notice that there's really no pattern. All the points are just kind of all over the place, and because they're all over the place, then that means we can say that that relationship is linear at this point. So that condition checks off just fine. The second test that we're going to look at is independence. And so the value of one truck should not affect the value of the next, so the observations are independent. Okay? Sounds fairly easy. We don't really need to look at that from that perspective. Our third test is normal. Okay? And this one, we're looking at the histogram. So the histogram of the residuals shows no strong skewness or outliers, and so the distribution can be considered normal. And again, it's second y equals instead of, we would make sure that we select the histogram right here and make sure that our X list is represented by our residuals at this point, and plot our histogram, and you'll notice that it really kind of makes a normal curve, so we should be fine there. Next, we're going to check the equal standard deviations. So since there are roughly the same number of residuals below the regression line as above, the standard deviations are approximately normal. So again, we're kind of looking at our residual plot right here. And when we're looking at this line, we're really checking to see, does it look like there's a lot more on top or a lot more on bottom of that residual line? And really, no, there's not. And so because of that, we can say that there's equal standard deviations at this point. So that condition checks off as well. And then we were told that the selection was random in the problem. And so that takes care of all of that. So our plan portion right here, it's a lot longer than it normally would be for a regression slope. But once we kind of work through all of that, then we are good to go with that. And then from there, we complete our do portion. And that's done. You can either do that the way that we just looked at it, or what you can do is come over here to Stat, arrow over to Tests, and then arrow down to G and find the linear regression T interval down here. Linear regression T interval. And then go ahead and you should have put in all of your data into L1 and L2. Make sure that your X list is L1, Y list is L2. Put whatever confidence level the actual problem calls for, and that's pretty much it. Just hit calculate, and it should give you everything that you need to know from there. We have our confidence interval right here from negative 0.2174 to negative 0.1084, and so that represents our confidence interval. And then also make sure to list your degrees of freedom as well. And then if I were you, I would try to keep it safe and include the formula for your confidence interval just for those AP readers. If not, just make sure that you state what test you actually used in order to find that confidence interval for that. And then finally, we just want to conclude. And so we are 90% confident that the true rate of depreciation of the Ford F-150s is between negative 0.2174 and negative $0.1084 per mile driven. And that's essentially how you would solve a confidence interval for regression slope.